Computer gremlins mess with us again, but whatever. It is what it is, right? So welcome. This is week one of a 4-week session. Jim DePalma and myself will be the instructors. Probably see a little more Jim than me throughout this 4 weeks, but we'll walk you through it. Brett's in the back, and Chris is in the back. They're going to be running the computer stuff for us. So session one of 4, and I have no mouse. Now I have a mouse. Awesome. So we're Wales Darby. You guys, I think a bunch of you have been on our webinars before, and we really appreciate it. So we are a manufacturer's representative company. Manufacturers hire us to represent their products. And throughout this presentation, you're going to see a lot of TACO, NTI. We're going to talk about a lot of different things, Centrotherm, Uponor, you name it. We'll get you up to speed on a lot of things. So what does this course cover? Session 1, the agenda will be advantages of using hydronic heat. Anything we put water through, we consider that hydronic heat. So we're going to go through some of that. We're going to talk about heat loss. We're not going to go into the weeds too deep on doing, let's say, a manual J. I know a lot of municipalities now are looking for a manual J calculation when you put your permits in to change out a boiler, for example. We're not going to go that deep. That would add whole nother week to our training. We're going to just stick to, we do a heat load calculation, and why do we do that heat loss calculation? We're going to stick more to that side of it. We'll talk a little bit about a new boiler or a retrofit boiler, right? You're going to replace a boiler. What's the right product for that application? Everything we talk about here is going to be getting the proper appliance for the application. It's very important. That way the appliance lives its full life and gives the homeowner what they're looking for. What to look for and why before you go ahead and change out a boiler. Usually there's some telltale signs when you walk into a boiler room as to how that system has been performing throughout the last several years. We're going to just touch on some industry terms. We need to make sure you're familiar with some industry terms, and we are going to give you some basic formulas. So later in today's program, you'll need possibly, whether it's a calculator on your phone, a piece of paper, something to write with, or a regular calculator. But we're going to do a couple of simple math problems, and we will be doing that throughout this whole course. So to get yourself prepared for this week, next week, and rolling forward, that's basically what you'll need in front of you when we're doing this course. And then we're going to talk about near boiler piping. We got a little mock-up of a boiler behind us. We'll talk about near boiler piping, what's on here, why it's there, what it does, and just get you familiar with the proper positioning of all these different items. We're going to talk about the size of the piping, the BTU it can carry. That's all going to take place throughout week 1. Give you an overview here. Week 2, you may have never done a system design in your life. Jim is going to walk you through a system design next week. We are actually going to probably email that out ahead of time, the system design, so you'll have it. You can print it out so you can work off of that sheet, and we will take and walk you through how you do basically, again, a little bit of coverage about a heat loss, but we're not going to do a full-blown heat loss. But we want you to understand where these numbers come from. So Jim is going to review that with you. So when we look at the outside of a structure, the envelope of the home, and it has windows and doors, you're going to understand what the values of those are. Okay, then you're going to have an opportunity to pick a cast iron boiler or a condensing boiler for that system design that you just built out. And then he'll review what the heat load calculation, what it would look like for heat distribution in our footprint. Jim will go through circulator sizing, and he'll also talk about what a system curve is. So
that's a lot.
Yeah, it's a lot. That is a lot. He's over there huffing and puffing already, but that gets pretty deep next week. So again, notepad, something to write with, calculator, and Chris will send that out, I believe, ahead of time on an email, so it wouldn't hurt to print out the layout, the form. Week 3, we were going to cover static pressure in a boiler system. We will put the myth to bed about static pressure in the height of a building, and whether that affects the size of a circulator. We're going to talk about where to locate the circulator. What position do I want it? Do I want it on the supply? Do I want it on the return? Because that's where they've come on boilers for years. Right now, you get them in a box. We're going to go through primary, secondary. We're going to take the myth out of primary, secondary. We're going to simplify that and just allow you to understand exactly what goes on between the closely spaced T's, whether you buy a manufacturer's header that comes with their piece of equipment or you build out your own. It doesn't matter to us. We're going to simplify that. We want it to be second nature to you. You know, when you look at it, we want it to be able to just click. System choice, zone valve or circulators. There's really no right answer, but we do put some, guidelines around whether it's a circulator job or a zone valve job, and we do that based on BTU, just because, where we see problem jobs, we try to get this out in front of you guys before you build out your own potential problem job. And root cause troubleshooting. So unfortunately, you guys are on the other side of the camera, I'm on this side of the camera, and we can't walk into a boiler room together. So what we do is we're going to put boilers up on the screen. We will give you a complaint from the homeowner, and based on what you've learned in week 1, 2, and 3, you're going to start to apply that information that you've learned and that you've gathered, and you're going to start to apply it to troubleshooting and getting to the root cause of the problem. The homeowner has a noise. Okay, let's find out what that noise is. The homeowner has insufficient heat. Let's drill down and find out why and come up with a solution. We want you to have the confidence, knowing and understanding that you can utilize a formula and figure out a lot of issues that go on in the hydronic world. Okay, it's the same formula we use on a daily basis. If you call us with a problem, we go right to that formula and we start to figure things out. So that's weeks 1, 2, and 3. If you're not burnt out already, we're going to go into week 4. We're going to do a quick review of 1, 2, and 3. We're going to go through low voltage wiring, the near wiring that you use around a boiler. Whether you're controlling circulators, whether you're controlling zone valves, we'll go through all of that low voltage wiring around the boiler, hopefully to make you a little more comfortable with that. And then we're going to do another deep dive into root cause troubleshooting. And again, we're going to give you the problem that the homeowner is complaining about, and you're going to use the information from weeks 1, 2, 3, and 4 and apply that to the root cause troubleshooting to resolve the problem and come up with a solution. Week 3 and week 4 will be very interactive. So we will be asking, right now, weeks 1, 2, obviously you got a question, please ask it. Jim is right by the computer to answer this stuff. But be prepared in week 3 and week 4. Get comfortable typing in if you want to practice a little bit now, and just tell Jim you're sending him a text message, a message as a test. On the right-hand side of your screen where that opens up, it drops down and you can go in there and ask questions. If you're going to take part in all 4 weeks, it's not a bad idea to get used to how that works and, fire off Jim some questions, or, hey, how you doing? And go from there. So Jim and I, we have goals here too, right? Our goal is to answer all the whys. And what does that mean? There's a lot going on in a boiler room, right? We want to answer all of those whys. Why is this here? Why is this here? What does this do? That type of stuff. We also want to help you understand the formulas used to design and troubleshoot hydronic systems. We are going to give you everything that we have. We have no secret, playbook when it comes to the boiler room. We're going to share all that information with you so that, you're going to be confident and comfortable trying to figure this out on your own. And if you're not, you need to reach out, you reach out, and we'd be happy to help you. We want you to leave our training with the information you came for. So if we are not covering something that you absolutely positively are looking for us to cover, again, shoot us an email, send a question, send just something to Jim saying, hey, what about this? And if we can fit it in, we'll fit it in. If we can't, we'll do a one-off with you, and whether we email back and forth, make a phone call, whatever it is, and answer those questions.
So just ask if we're going to be covering any radiant. I said, yeah.
Yeah, we're going to be covering radiant for sure. Yep, Jim will have that. Actually, next week you can put that into part of your design. Okay, so again, this is all about what you guys want to do. We do have a radiant class that's a standalone. So if we don't cover enough radiant, you reach out, we'll set it up to where we can do a full-blown radiant. So with all that being said, it's a hefty lift there, so be prepared. Have the tools you need at your desk wherever you're doing this, because the more you put in, the more you're going to get out. So the question is, why do we sell hydronic systems, right? Why do we sell hydronic systems? We are all in the comfort business. That's what we are. We want to make sure that everyone is comfortable within their homes. And our goal is to make sure that if we go in and do a replacement that, looks like this, that is going to give the performance that the homeowner is looking for. Okay. And some of the main reasons: we provide heat through convection and radiation. So that is, we're going to be, talking about baseboard. Some of the terms I will use throughout this course, you're going to hear me say heat emitter. If I say a heat emitter, that is anything that's giving heat into that facility, whether it's a room, whether it's a garage, whatever. If it's a baseboard, that's a heat emitter to me. Whether it's let's say a Modine hot dog hydronic heater in a garage, that's a heat emitter to me. So you'll hear me say heat emitter throughout the course. That's what I'm referring to. We limit heat loss from your body. Okay, so I'm standing here, I'm moving a little bit, I'm probably giving off 500 BTU as I'm standing here. Everyone else in the room here, if we're just sitting still, you're probably in the 400 BTU range. So when we lose that energy, we need to replace that. So with hydronic heating, we limit the losses of that body heat, so we feel more comfortable in the space. Design flexibility, easy zoning, right? We can do from mild to wild with zoning. It doesn't matter. We can do it. I always put up here improves air quality, and with COVID going on, whether it's real or not to you, whatever. But it doesn't really improve air quality. But what I put here is, if I have a house upstairs with baseboard, let's say I have 3 bedrooms up there and someone's ill, and we just kind of open a window in a room, shut the door, and isolate them from the house with a warm air system. If I ever return in that room, which I should if it's done right, I'll be picking up all the germs, putting out throughout the rest of the home. With a hydronic system, we're just going to be flowing water through that baseboard, and hopefully we can isolate that to a room. So that's what I have up there by improves air quality. It's not like, there's some magic wand in there that's going to make air quality better, but that's what I mean by that term. All right, quiet, even heat. So if we do this right, it's really quiet. It's nice and even. I feel the same walking through the whole house. I can zone it to make sure I feel the same walking through the house, and then I can zone it in other areas of the house where I may want it a few degrees cooler. So I'm not going to experience huge temperature swings in my controlling of the heat. Usually within 1 to 2 degrees, I can keep a hydronic system operating. Efficient systems using less fuel and using less electric. We'll dive into that a little bit deeper here, whether we're talking about a super efficient condensing product, whether we're talking about using ECM type circulators, DC driven circulators that are more electrically efficient, whether you have an old oil burner and you're using a constant ignition transformer, or if you put a control on there that drops an ignition out after it ignites. So a lot of different things there that we can look at as far as from a savings perspective. Flexibility, one source. I have one boiler. I have one set of near boiler piping, and I can go ahead and I can heat the home. I can have multiple temperatures. I can have multiple zones. Okay, I can heat domestic water. I can do snow melt. I can heat my pool. I can heat my towels. You name it. With hydronic heating, if we can get a pipe to it, we can probably take care of that need. So typical hot air system, you got one temperature of air coming out of the registers. Okay, here, depending on how many zones we could have, several different temperatures. Let's leave it at that. I don't want to dive into that too deep, but we could have several different temperatures just by controlling it, whether it's a mixing valve, whether it's an I valve, whether we have a zone that's controlled off of outdoor reset, a lot of different ways we can do it. So we have two different considerations here. Here's Bob the builder up on the roof. He's building this new house, and we could be looking at potentially going in and doing a heating system for that new home. Or, we could get a phone call from this person who has a house built out of pallets, and we could be looking at going in and doing a retrofit and changing out a boiler in this home. So what are some of the things we need to do here? We need to do some type of a heat loss calculation. Obviously, the heat loss in this home is going to be substantial. The heat loss in this home, after talking with Bob the builder, you'll know, what the heat loss will be in this home, whether it's going to be a spray foam, whether it's going to be Pink Panther. It doesn't matter, but we need to do a heat load calculation. Right soft, manual J, we don't care what type it is. We just want to make sure that you're doing a heat load calculation, because reality is that's your best tool. Majority of the boilers you're going to run into in the field are oversized, and you're going to find that some of them are grossly oversized. What improvements have been done to the home? So there's a lot of things that go into, new and or replacing. This is just a diagram of Taco's program. It's a Flow Pro. Again, we don't care what one you use. We just want to make sure that it meets the needs of the end user, the homeowner. So new and or retrofit. So we have condensing on the left here. We have cast iron on the right. And you're going to look at, jobs like this. Do I replace that with a condensing product, or do I go back in there with a cast iron product? That's going to be a conversation that's going to be had with the person that is asking you to replace this piece of equipment. So here we have Bob the builder up on the roof. We have the conversation with him, and the conversation looks like this. Does he have the heat load calculation? Yes or no? If he does, great. If not, somebody's going to have to do that, whether it's you, the engineer, whoever is on that home, someone has to do that heat load, or we are lost at that point. It's always good to understand the type of heat emitters that they want in that home. Is this going to be a hydro air system? Normally with hydro air, we would run a little higher temperatures unless you're really, really focused and driving the temperature down, which is a great thing to do. But majority of the time, if we're looking at a hydro air type system, we're looking at higher water temperatures in our boiler system, and this is something to keep in mind next week when you're doing your design. I put on here insulation value / type. That becomes an important factor. Am I using just standard, R13 or an R38 or R40 in the attic? That's important. Am I getting spray foam? Is it open cell? Is it closed cell? So let's say, he's building that home. It's going to be extremely tight. You're going to go in there and put the heating system in, and someone needs to address that. We now have this super tight home, and whether it's going to be an HRV or an ERV system that needs to be installed into that home to exchange air to make sure we have a healthy home, that's a conversation that has to be had. And then we really want to understand the customer's expectations. You're going to go in there, do a heat load calculation. You're going to ask about the shower. How are they going to make hot water? So you go in there and do your standard install. Let's say it's a boiler and a 45-gallon indirect. Great. Then we find out the customer puts in a 20-gallon a minute shower head, and that system no more is adequate. So we really need to understand with the builder or the homeowner what's going on and what are we replacing, and what do they have planned for the future if they're going to do a retrofit on their bathroom or something. Here it is, the old cast iron. Probably started out its life as an oil burner, ended up its life as a gas burner, and you're there ready to do a retro replacement on this job. So what do you need to know? It's really good to know if there's a rating plate on the boiler. If there is, take that rating plate. This way here you have one gauge as to the boiler sizing. If the boiler doesn't have a tag on it, you can look at that burner. Maybe the burner has a tag on it and it tells you what the input is. If you have absolutely nothing in the boiler room, okay, fine, we get it. It happens. Probably not a bad idea to go around and measure the radiation. That would be good. You can clock the gas meter, and that tells you how much gas the unit uses. Doesn't really give you the proper size. You could take the nozzle out of the oil burner and look at the nozzle size, and if it's a 1 gallon nozzle and it's a 100 psi pump, you burn 1 gallon per hour, and all that tells you really is how much oil it burns in an hour. It doesn't tell you if it's the right size for the home. You could look at the gas orifices, same thing. You know, there's books out there. If you give boiler dimensions, it could tell you the BTU. That really doesn't get it done. So back to that heat loss calculation, you have to do a heat load calculation on it. It's critically important to make sure you're sizing this right. And then after you do the heat load calculation, it's always important to understand what changes have been made to the home. Have they made the home more energy efficient? So the heat load calculation will do that for you. So you could be looking at a 150,000 BTU boiler. It's in the basement currently, but they've, you know, sided, they've insulated, they put new windows in, they've put new doors in, and now the envelope heat load calculation may be 90,000 BTU. So very important to pay attention to that. Before you remove the old boiler, especially if it's an old cast iron boiler, always look at the aquastat setting on the boiler, the temperature setting on the aquastat off the old boiler. And that's important to know because if that's set at 200 degrees or maybe a little bit above 200 degrees, that is critically important because there are condensing products out there that really may max out at 176 degrees. So if you needed 200 degree water to satisfy the load within that home, 176 is not going to get it done, and you're going to be underheating that home. And then if you hook outdoor reset up to it, you're really going to be underheating that home, basically the life of the boiler. So important to know that. The type of heat emitters, that's important because that plays right into system conditions. So if I have an old cast iron system with big 2-inch diameter pipe and I'm going to put a condensing boiler in there, that's a good marriage. Large volume in the system, low volume in the boiler, that's a good marriage. But how do I treat that? How do I treat the water? How do I treat those pipes? How do I get all the dirt and debris out? That's important. So when you're going in there and looking at these, we want to make sure you're successful with your boiler changeouts. These are just some of the items that you really need to understand. And then customer expectation. You could go in there, change out a boiler, do the absolute most beautiful piping job, and everything is picture perfect. That boiler room job may not fix the problems that were going on within the home. Okay, when the person put the baseboard in, they only drilled the 7/8 or whatever, a 1-inch hole, and you got 7/8 pipe going through there that's expanding on outside diameter 7/8, and it expands and it creaks. I don't know that we're fixing that problem in the basement, right? If they don't have enough heat emitters in a room, we probably are not fixing that just by changing out the boiler or working in the basement. So have that conversation with the homeowner, know what their expectations are, know what their current potential problems are, and see if you can address them with changing out the boiler. Heat load is king. And why is the heat load king? If we oversize a boiler, right? The old method used to be you'd walk across the street, you know, go like this, and if 4 fingers covered the house, that was a 4-section boiler, right? If the boiler had a coil in it, if it was an oil boiler, it had a coil in it, and it only needed a 3-section worth of BTU, you'd put the 4-section in because you wanted the additional BTU to drive the coil. So don't make these assumptions. If we oversize a boiler, it's going to short cycle. What does that do? It drives up the fuel bills, premature component failures, and just higher service and operational costs. We don't want that for anyone. And don't guess. Don't just say, you know, that boiler's twice the size it needs to be. We're going to put in this because this is what I do every day, and it works. If you undersize a boiler, it's going to inadequately heat the home at design temperature or maybe more often than that. Back to that dirty system where we're going to put this, you know, condensing product in. And if you go through and read the manuals, it doesn't matter if it's on a cast iron product or on a condensing product. They're going to tell you to flush the system. Okay, now in the last 10 years or so, we've been introduced to a lot of these different cleaners. They're on the marketplace. We don't rep a cleaning company, so, you know, nothing to do with us here. but there's different brands out there. You look at the manufacturer, the boiler manufacturer's literature, they'll probably recommend 1, 2, or a third brand to put into the system that will clean the system so that that dirt and debris does not make it back into your boiler. We also have, you're starting to see out in the field a lot of these dirt and magnetic separators, as we have here on the return. So that would grab the dirt and magnet, anything that's metallic in the system. It would grab it right here with this magnet, and we have the ability to blow it off and get it out of the system. So that's another way. Just be cautious of what you're hooking it, what you're hooking to, what are you tying into. So that's kind of what you're going to look for when you walk into a boiler room, right? You see what you have, and then you're going to start to make some decisions. Now we're going to get you up to speed on some terms here that are going to be used throughout the course. And week 1 is just kind of getting the ball rolling here, so just bear with us. BTU, British Thermal Unit. That's the amount of energy needed to raise 1 pound of water 1 degree Fahrenheit. Okay, everything we talk about is going to be driven around these terms. BTU. GPM, gallons per minute. You're going to hear that constantly. That's going to be in a formula here in a little while. Get familiar with that. The little triangle right there with the T, that's delta T. That's going to be the temperature difference. And Chris, I'm going to have you bouncing all over the place with the camera here. But if this is my boiler and this is my supply header, if I leave this supply header at 100, and we'll use old term numbers, 180 degree supply, the goal is to go out through my heat emitters, come back on a design day at a 20 degree difference. So I would go out to my supply to heat my home. I would come through all of my heat emitters, come back down here to my return piping, go back into the boiler to be reheated. And the target number that we look for with cast iron is 20 degrees. We'll touch on that a little more. Flow rate, GPM, we said that. Flow velocity, this is feet per second. There's a formula for that. We're not going to give you that formula. That one gets a little crazy. So we're going to give you something that's even easier than that. AC current, that's what we're using right now for the most part. Looking for a 007, standard 007. I thought we had one here. I don't know, maybe we don't, but if we do, we'll just show you a standard 007. That's alternating current. That's what we've been using in the hydronic world forever. Here we're looking at a 007 with an E at the end. This is a ECM. So this is a DC driven circulator. You put AC power to it. In the board here, it converts that power and drives this circulator through a DC driven motor. And what does that do for the end user is that's part of that electrical efficiency that we were talking about early on. So here's our, this is our bread and butter, right? This is what conquered the world for Taco, is this 007. And now we're slowly starting to see it replaced with 007Es. And the reason for that is this is like running an 80-watt light bulb. 2,500 run hours in your typical heating season is how many hours a circulator runs. So by switching to an ECM, it will run the same amount of time because that's how much run time we need to support the house. But this will run up to 85% more efficient than the standard 00 will, or the red one, or the purple one. If we're talking AC, it's like running an 80-watt light bulb. So just think of it that way. Here, we're running a 44-watt light bulb down to, let's say, 10, 12-watt light bulb, depending on the demand. So just so you understand what's going on internally with these circulators. AFUE, AFU ratings. This is the annual fuel utilization efficiency. Those tests are done at 120 and 140 degrees. So when you see all of these condensing boilers out there to tell you that, they're 92, 93, 94, 95% efficient, they are at those temperatures. But as we start to accelerate those temperatures up, the efficiency will drop. If we bring those temperatures down, the efficiency will actually go up a little bit. You can get close to 98% efficiency with lower water temperatures. So we want to make sure you're 100% up to speed on how this works and what's behind the numbers. So how do we know what's behind the numbers, and what do we use to figure out what's behind the numbers? This is the formula portion of the class. So this is the universal hydronic formula. Everything in the hydronic world lives around this. And I say that we use this every day. I mean, it's an everyday thing. I'm looking at Jim, he's smiling. We use this every day. And we try to hand this out as often as we can. So if you want to take a snapshot, screenshot of this, treasure this piece. What is this telling me? GPM. We just talked about that. That's gallons per minute. Equals BTUH. That's our load, right? That could be our boiler capacity. That could be a heating zone capacity. That could be anything that needs BTU. Okay? That does not have to be. We don't have to use this formula in only one type application where all I care about is the size of this boiler. That's not necessarily the only. That's definitely not the only use of this formula. And then in there we have a dividing sign, and then we have parentheses, which has our delta T symbol and 500. So the delta T symbol, that is going to be what we are looking for, a temperature difference across that boiler. And I said earlier about a 20-degree delta T. So 20-degree delta T will be the most common temperature that we're going to be using in the hydronics world. We do have a 10-degree delta for radiant. We do most of our designs for radiant around 10. With condensing boilers, you may have a 30-degree delta designed around that condensing boiler because we want it to condense, because that's where they become more efficient. But for today, we're going to stick with a 20-degree delta T. So 20-degree delta T is our number. Write that down. We're going to go back to that. Going down through the formula here, you see at the bottom it says 500 equals 8.33 times 60 times 1. What does that mean? These are just numbers. What does it mean? Well, we know a BTU changes water temperature, right? 1 BTU, 1 pound, blah, blah, blah. So how do we do this? We have to put a timing mechanism in there. So we look at it over an hour. So 60 minutes is an hour. We take a gallon of water. A gallon of water weighs 8.33 pounds. So 8.33 pounds multiplied by 60 equals 4998, I believe.
Yep.
So instead of using 4998, we round it to 500 because that's much easier for guys like me that have to do math. So 60 times 8.33 equals 500. Your calculator's not going to tell you that right now, but I am. So again, it doesn't equal 500, but we're going to use 500. So just joking. On the end there, you see a 1. That 1 stands for straight water. If I use straight water in a system, I have this boiler right here, and I'm going to use, just a water system. I have no need for antifreeze, no need for anything, just straight water in that system, which is a vast majority of the systems out there. That's your formula. 60 times 8.33 equals 500. And then we have the other side of the coin where we may need some antifreeze in the system, whether I have an air handler in the attic, whether I have a radiant system that's tied to the boiler, whether I have, pipes that go out into my overhang and go up to the second floor that freeze every so often. It's annoying, so I put antifreeze in the system. That changes things a little bit. Antifreeze wants to reject the absorption of heat. That's why we use it in our automobiles, right? We want to take that heat out of the engine and get rid of it through our cooling system. So what we do here is that 1 is going to be used as a factor. And if you have a 5-gallon bucket of antifreeze or you have a gallon jug of antifreeze, on that gallon jug or 5-gallon pail, it will give you a factor. And I believe we sent out the TACO catalog to everyone. If you go into, I think it's page 44 or 46, it will give you a 30% glycol, a 50% glycol mix within that book. So on that pail, you take that factor and you factor it in, and what you're going to find is that 500 no longer becomes 500. It will be a lower number. So the ability of a gallon of liquid in your heating system now has less ability to absorb heat and deliver heat. And that's what this formula is going to help us figure out here. So let's just assume this is my boiler and it's a full water system, no antifreeze. Every gallon of water that I run through this boiler and I send out of here has the ability to carry a delta T times 500. Cast iron boiler, 20-degree delta T times 500 equals 10,000. So that tells me every gallon of water, thank you, Jim, every gallon of water within this boiler has the ability to absorb 10,000 BTU. Every gallon of water within this system has the ability to absorb that BTU. So as I'm sending water out of here, I'm flowing water out of here, GPM, right? GPM equals BTU divided by delta T times 500. So now that delta T times 500, I just told you that's 20, so you could write 10,000 BTU above that. So I now have heat going out at 180, let's call it. It's going out through my heat emitters. It's coming back at 160. This boiler now has the ability to elevate that water back up that 20 degrees to send it reheated out of here to keep the BTU cycle going. We're producing BTU in the boiler. We're putting the BTU into the home through our heat emitters in the rooms. That's what's taking place. So to go further with this formula here, GPM equals BTU divided by delta T times 500. So if we want to use this formula, and I have 10,000 right there above my delta T and 500 sign, and I tell you that this is a 100,000 BTU boiler, please do the math. 20 times 500 is 10,000. 10,000 divided into your boiler size, 100,000 BTU, and send Jim the answer. What is your gallon per minute flow rate required to support this 100,000 BTU boiler at a 20-degree delta T? So Jim is going to sit there and he's staring at the computer and he's actually giving me a thumbs up. So that's good. We had at least one response. We know one person out there is alive and kicking. It's awesome. And he got it. Good.
We got two.
There's two. And keep them coming in. And if you don't understand how we're getting to that number, please also let him know, because you have to get this in order to be successful in week 2, 3, and 4. So basically what that formula just told us is, if I know the BTU of this boiler and I know the delta T times 500, I can figure out what the flow rate needs to be to support this boiler and the piping. We'll go through the piping diameter in a little bit, but you'll be able to figure all that out. Okay? That is one way to utilize that formula. The other way to utilize the formula is, if I know 2 of the 3 in that universal hydronic formula, if I know 2 of the 3, I can figure the other one out. And it's either going to be, I'm going to multiply or I'm going to divide. We just did the one where we divide. We just did the divide. We took the delta T times 500, divided it into the boiler size, told us that we had a 10 gallon a minute flow rate. If I know the flow rate of this circulator, and let's say I look at the piping, I'll give you a chart here in a minute. If I look at the piping and say, you know, this is going to be 3 to 4 gallons a minute, let's say 4 through 3/4 pipe. So 4 and 4 is 8 gallons a minute. So 8 gallons a minute, it's a cast iron boiler. I'm going to calculate a 20-degree delta T. So now where my GPM is, you can put an 8 over the top of that. You can take the 20 times 500, still equals 10,000. Now I'm going to take my 8, I'm going to multiply it by 10,000. That tells me that I should have at least an 80,000 BTU boiler. So you can utilize that universal hydronic formula two different ways. We can multiply or we can divide. And over the next couple of weeks, you will be using this universal hydronic formula. You will be multiplying. You will be dividing. We will give you a 10-degree delta. We will give you a 20-degree delta. We will give you a 30-degree delta. And all you're going to do, if it's a 10-degree delta in that formula, where the delta T symbol is, you're going to put a 10 there. You're going to multiply that by 500. Now every gallon of water has the ability to carry 5,000 BTU. If it's a 30-degree delta T, you're going to put a 30 where that delta T sign is. You're going to multiply 30 times 500, and you're going to find that now you can carry 15,000 BTU with that gallon of water. But majority of the time, when you're using this formula, you're going to put a 20 where the delta T is, multiply that by 500, and that gallon of water has the ability to carry 10,000 BTU. I just want to check. I want to make sure everyone is clear on that. If you are not clear on that, please let Jim know. We're not going to blast your name out there or anything else. Send us your email, your phone number if we need to reach out to you after the class to make sure you're on board with this, because believe me when I tell you, if you don't have this, you're going to be lost the next few weeks. So here to break it down, the weight of 1 gallon of water is 8.33 pounds. Multiply that by your hour, and again, that 500 becomes a constant. You will see that in another formula that we're going to go over here in a bit. So, formula you should know. There we go. That's it. We'll break it down one step further. Gallon per minute equals load divided by 500 times delta T. So here we have a 20-degree delta T. With that 20-degree delta T, we're always going to do the math in the parentheses first. 20 times 500 equals 10,000. 10,000 divided into my 100,000 BTU boiler gives me my flow rate of 10 GPM. That's the example we went over here live. I hear typing. We good, Jim? Everybody's good?
No, good question. One gentleman asked, is the radiator delta T the same as the baseboard? My response was, well, yes. The delta is really for the whole system.
Yep.
And somebody wants to know, can you go back to the last slide?
Absolutely. Right there. If you know the BTU required and the design temperature difference, delta T, the GPM flow rate required can be calculated. So that's either we're going to multiply or divide. When the GPM flow rate is established, the pipe and circulator size can then be determined. So if I have a 1,000,000 BTU boiler or 200,000 BTU boiler, I can't pipe it in 1 inch, and we'll get to a pipe chart here shortly that'll tell you what a 1-inch pipe will carry. So when we start to build out these systems, you know, I like to always check it 3 ways, do my manual J's, you know, I'll measure the radiation, I'll check the boiler, I'll check the near boiler piping. I was just on a job with a contractor the other day. They got 2 boilers. We walked in. They have a 2-inch header, which will support both boilers' BTU, but they have an 1.25 inch return header, which only carries 140,000 BTU. This is a boiler system. Every gallon of water that leaves has to come back. The BTU that leaves has to come back. It's going to be BTU just at a cooler temperature. This is not like a hot air system where as I have takeoffs coming off of my ductwork, I can then slowly reduce my ductwork. Whatever header comes out of here, I need the same size header on my return because the same amount of BTU is coming back. It's just coming back at a lower temperature. So it's all about flow in a hydronic system. That answered the question, hopefully?
Oh, yeah. Yeah.
Great. So most common delta T's, here we are. Again, there's a cast iron boiler. I don't care what color that jacket is, guys. That's cast iron. It's designed around a 20-degree delta T. I want to see if my laser will work. Okay, so here's the supply header. We're going to be coming out of here. We're going to go out, go through our heat emitters, up through our heat emitters. We're going to come back down, and we're going to tuck into this return pipe right here. We're going to go into this cast iron heat exchanger. Underneath here is where the burner is. The flames are going. The water's coming in. It's circulating across those cast iron sections. It's heating up, and then it's coming back out 20 degrees cooler, or hotter, I'm sorry. And that is all done by design through the size of the circulator, the size of the piping, and the capability of the boiler. the BTU of the boiler. We're exchanging the energy that the flame source is making up through the cast iron sections. We have our flue passageways, and then we have the waterways on the other side of the flue passageways. We're exchanging that energy back into the water, sending it back out to the house to heat the home. Additional items here with calculated most of the time for 20-degree delta T's: baseboard, convectors, Modine hot dog, NTI indirects. You could see up to a 30-degree delta on the indirects. Plate exchangers, we start out normally designing them with a 20-degree delta. Most of the time, you could see those vary, but that's about where we live, for out of the box. That's where we start. So almost everything we work with, again, is designed around that 20-degree delta. So this right here, this is just going through and letting us understand the ability of a pipe to carry BTU. So the most common size pipe we see for baseboard heating is 3/4 inch, 3/4 supplies right here. That goes out to 3/4 baseboard heat circuit. We can have 67 feet of a 600 BTU per foot piece of baseboard heat emitter hooked to that 3/4 pipe. And if we did 67 times 600, I believe it's going to be 40,200 BTU, and a 3/4 pipe, which you will see in the next slide, has the ability to carry comfortably 40,000 BTU. So that would be properly sized, right? This is what we use daily. These are the pages that we use on a daily basis, obviously not in the middle of summer, but during heating season, when guys call and ask, this is what we live by. If I have 80 feet of baseboard on that heat circuit, I am going to use up the ability to put 600 BTU of heat energy into the home per foot of baseboard, per linear foot of baseboard. So just keep that in mind when you're designing and sizing. This right here is very important to have this. I would screenshot this if you don't have it already. This goes through a pipe size from 1/2 inch copper, 3/4, 1 inch down the line, all the way up to 2 inch copper, and then we go ahead and get into iron pipe, so you have an understanding at a typical delta T what a pipe will carry. We find the most common header size off of a boiler is 1.25 inch, and if that is the case, and you install a 200,000 BTU boiler, and you can see here at a 20-degree delta, 1.25 inch pipe carries 140. That becomes your roadblock of getting the heat out of the boiler. And if you are short cycling that 200,000 BTU boiler, this may explain why. Okay, you can't always go by the pipe diameter that the manufacturer has exiting their product. Most cast iron manufacturers go to the largest diameter size because those sections are used across their whole run of boilers and BTU range. Most manufacturers on the condensing side will have a smaller diameter pipe coming out of the bottom to carry the BTU load, and you are expected to increase that pipe. And the reason it's smaller is because inside of this box, there's not a lot of room for large diameter piping, so they will normally calculate the piping into the head loss of the heat exchanger, and then when you exit the boiler, whether it's top, bottom, or side, you are expected to increase the size of the piping in order to support the BTU that boiler will produce. Jim has a question.
Yeah, good question here. When would you use a 30 or a 40-degree delta T? When would you design a system that way?
Okay, so I'm a fan of designing a condensing product at a 30-degree delta, and I may only do the boiler circuit at a 30-degree delta and then do the system circuit at a 20. The reasoning behind that would be I want this boiler to condense as much as possible, and I think we'll touch on it over the next couple of weeks, but every gallon of condensation is 8,080 BTU of energy that is staying in the home. So the more I can make this condense, the more efficient this is. I joke all the time when we have a live class because you got to keep guys from falling asleep, right? Which maybe I have to do that right now too. But I always tell guys, this is a vending machine. I take a dollar bill out of my pocket and I tuck a dollar bill into this vending machine, my boiler. 95 cents of this, it tells me on the sticker that I could have 95 cents of that stay in my house and only send 5 cents out of my polypropylene venting. That's my goal. Well, how do I do that? I have to make this condense in order to do that. I go here to an 80% cast iron product. I take that same dollar bill out and I feed it to my boiler. And if things are running good, 80 cents out of that dollar are going to stay within my home and 20 cents are going to be going out of the flue pipe. I want to keep as much of that in my house as possible. So sometimes I'll design the boiler circuit at a 30 to make it condense more. And also on a 30 and 40 degree delta, most of the time it'll be a commercial type application on a 40 degree delta, but just take a look at the BTU that a 2-inch pipe can carry. I'll go with iron. So iron, 20 degree delta, I can carry 500,000 BTU comfortably. 40 degree delta, I can carry 1 million BTU comfortably in that pipe. So if I have a very large, let's say it's a school and I have multiple cast iron boilers or whatever boilers in there, I may want a larger delta T so I can reduce the size of my pipe. That's some of the reasoning for why we go to greater deltas than 20.
Some good conversation popping up here. So the same gentleman who asked the question said, basically came back with, so for a condensing boiler, I'm going to use a 30, but cast iron will use a 40.
Commercial cast iron, on commercial cast iron, you may see up to a 40, and that's strictly driven around the pipes, but you may also see on that boiler, you may see a crossover with a circulator just to protect the iron a little bit better, but the system may have the 40 because we want to use smaller diameter piping. Maybe I didn't explain that properly, but that's what we're looking at. We still have to protect the cast iron.
So another gentleman made a very good observation. He goes, so basically for every 80,000 BTU boiler I've seen piped in 3/4, it's only a 40,000. Excellent.
I didn't say it, he did. Okay, I didn't say it, he did. Yeah, but that's, look, we are giving you best practice, right? That's our job. We give you best practice. The speed limit on the New York State Thruway is 65. That's best practice. I'm not telling you to do 65. I'm not telling you to do 55. I'm giving you best practice. That's what this chart is. If we average those flow rates, that is the BTU you will move through that pipe. You can go find another chart that will give you a number that you may want to see. I mean, it's not uncommon to see 1-inch pipe carrying 90 or 100,000 BTU. It will just skew your delta T a little bit. And when we talked about feet per second earlier, velocity, it will skew the velocity, and we'll talk about that. So this is a very safe, conservative chart. If you do the install and you adhere to these numbers, you will not be back there for a problem with flow, with noise, with erosion, and you will deliver the BTU that this tells you.
I mean, snow melts, they start at 25.
Right, snow, right, there you go.
Bigger, we want to go to a 30 to keep pipe size as
small as possible. Yeah. Right, yeah. So again, this is best practice. This is not for every single install. Radiant, we said we design for 10. That's if I'm in your living room, I'm designing that for 10. Jim's doing the design for a snow melt, it's going to start at 25. Or you're going to end up with, 2-inch pipes in your driveway to melt the snow. That's just not practical. So that's where this comes from. And great debate, great questions. Keep them coming. We love it.
I mean, so here's another one. So we can fix the home not heating well by just changing the pump, increasing the delta T.
No, a BTU is still a BTU.
Yeah.
A BTU is still a BTU. Yes, a 15-degree delta T, a gallon of water has different abilities, right, at a 30. But if I don't have the heat emitters, and that goes back to when I said make sure you remove the cover off the aquastat on that cast iron boiler before you replace it. If I look at baseboard heat at 200 degrees, I may get 600 BTU per foot. if I look at that same exact piece of baseboard per foot at 170 degrees, I may only get 530 BTU per foot. So be cautious here. Changing the delta T doesn't necessarily, it's not going to deliver more BTU. A BTU is still a BTU. This just gives us the ability to basically make a boiler rain a little better, use a little smaller diameter pipe in some applications. I think you'll probably end up running across this in week 3 when you're doing your boiler room troubleshooting. So great conversation. Keep it coming. We love it. I'll keep rolling. Again here, this is just giving you your flow rates and minimum and maximum velocities. And what do we mean by that? We need to move water at a certain rate within that pipe. And our goal is 2 to 4 feet per second. We do not want to really exceed the 4 feet per second because we'll get into other things. But we need to have a minimum of 2 feet per second, because if I have a pipe going uphill and I have these tiny little pain in the neck air bubbles in there, if I'm not moving that water at least 2 feet per second, I don't have the ability to move those air bubbles within the system. Let's say I'm at 1 foot per second, those air bubbles will stay attached to the pipe, and then they're eventually going to work their way up to the second floor, and they're going to have an air party, which means you have a service call to go bleed that circuit. So there's minimum flows we need to adhere to. There's maximum flows we want to adhere to. We want to make sure we're moving the pipe at the proper rate through these different heat circuits to make sure that we move any entrained air that may be out in that system. So velocity below 2 feet, I cannot move the entrained air. Velocity at 4 feet, that's like my limit. I will slowly start to cause a little bit of noise. At 6 feet, I will absolutely create noise. At 8 feet per second, I can actually erode pipe. So if you're on the second floor and you have a hole in an elbow and you're blaming the elbow, you may want to walk downstairs and look at that V8 circulator that's been hammering on that pipe for several years, and it may have just wore out the pipe, and we're moving water too quickly. So we're creating erosion within the pipe, which leads to that magnetite and that dirty system and all that stuff we talked about right at the beginning. So this is a system, and we address it like a system, and that's why next week you're going to actually design a system so you could see it starting from the boiler room, what the near boiler piping would look like, all the way up through your heat emitters and back to your boiler. And we want to make sure that we're sizing that properly. You know, we're probably going to end up putting either circulators or zone valves on that system. That'll hinge on how much time, and you'll calculate what size the circulator would need to be, and you'll calculate, you know, whether it's a zone valve or circulator job. We good, Jim? You're typing away? Everything's good?
Getting great questions.
Good. That's what we want. And multiple guys, so everybody's learning how to type in and ask, because when we get in next couple of weeks.
2 guys.
Okay, great.
Yeah. I mean, there was one where, you know, depending on the length of the board, from 67 feet to 109 feet, would you round up the delta or down? And that's not really what we can do.
Right.
You know, our goal is to try to get a system design. If whatever our delta is going to be, if it's going to be a 20, great. And if we can make that at design, great. But as the outdoor temperature changes, our delta within our system is going to change regardless.
Right.
We just, in our design factor, this is where we want to head.
Right. Yeah, we just want to get close to those numbers. We're not saying you have to adhere to those numbers perfectly, because we could throw another wrench into it to really make your guys' mind start to spin. We talked about this little 007 before, right? This is our bread and butter. This is what Takeo cut their teeth with. This is a constant velocity pump. This is a P pump. It's going to have the same operating pressure. It's going to have everything the same throughout its whole life. It's going to have the same flow rate, everything throughout its whole life. So if I put that circulator here and I have 2 zones open, it's running at full speed. If I close one of these zones, it's still running at full speed. So if you go to this ECM circulator, which a lot of boiler manufacturers have, I will stay at the same head, but if I have both of these open, the circulator will be running at full capacity. If I close one of these, the circulator has the ability to reduce its electrical usage, which will reduce the flow rate a little bit. It's not going to marry up perfectly to the pipe like our VT temperature sensitive circulator will, but it will reduce the flow a little bit. So that will throw even another wrench into this. But if we stick to that piping diagram with the 2 to 4 feet per second, that's really important, and it will definitely give you a great designed and operating system.
We got some thinkers on here. A couple guys were saying, hey, if I use PEX pipe, can I erode if I go over 4 feet?
Absolutely. Yeah. So great. That's awesome. And if you're doing open or expanding pipe, you're going to get more flow rate through that than you would through a crimp style, because the fittings, the pipe diameter is the same, but the crimp fittings, you're going through a much smaller opening in the fitting, which will reduce your flow rates. So this is all stuff you guys need to be aware of, right? Especially when you run into a problem job, and the problem job is insufficient heat, but everything looks good, and then you find it was switched over to PEX after it left the boiler, and it was crimp style. Now we've just reduced. So I said 67 feet of baseboard, 3/4 baseboard at 600 BTU per foot. That's copper. If I go to an open ore, you're probably in the 58 range. If I go to a crimp style, you're probably down, in the high 40s of ability to hook the linear feet of baseboard to it. We good?
Yeah. One gentleman wanted to he just asked, and this is interesting, where can I see all the questions?
Oh, yeah, right, yeah.
I'm thinking where he's going. He wants to.
Well, yeah, I mean, throw if you want. Since we're so interactive, this is like the most interaction we've had in quite a while. Just read the questions aloud, as we go.
Well, that's what I've been doing.
Yeah, good, perfect. We'll keep doing that.
Yeah.
Excellent. Thank you, guys. This is great, and girls, who's ever out there, ladies, we appreciate it. Okay, so this is an indirect hot water heater. This is going to be a recovery time formula. So we said we were going to give you a few formulas this week, and we are. And I know this has been a common question that has been asked to me, so I put this out there. I've actually done, Jim and I do this class live, and we have 30 guys in the room, and there's always one guy in the room that comes back and says, now I understand why I don't have, by the time I get in my shower for the second or third person, I understand why I run out of hot water. And it's always amazing to me when I go to an install and, we're the NTI guys, we go out on, let's say, an NTI with an NTI indirect, and we helped him lay out the piping. It's his first NTI, let's call it. And he says, holy cow, this thing made hot water in less than 10 minutes. Yeah, that's what it's supposed to do, really. But, so that's no great shakes to us, because we understand the performance. And if I pipe it and pump it correctly, that's what it should be. 10 to 12 minutes on most of your standard indirects from a cold start. So because we don't see that often, we want to give you guys another formula. So when you get questioned by the homeowner, hey, I get 2 showers out of this 40-gallon indirect, why? I want to answer the whys. So in this formula, RT, that's recovery time, equals domestic gallons, so that's the indirect, times domestic delta T times 500. There's that 500 again. And then we're going to divide that by the BTU of the boiler that's tied to the indirect. So what does this look like? Recovery time, 40-gallon indirect. Most tank manufacturers, whether it's a direct fired water heater or a indirect, they have the ability to call it a 40, but they only have to adhere to 40% or 80% of what they call it. So most 40-gallon indirects actually hold 36 gallons of water. So I'll bring in some numbers here. So delivery temperature, I want to deliver the water leaving that indirect at 115 degrees to the home. The incoming water to the home is 50 degrees. So that's in parentheses, right? So we're going to do that math first. There's our 500, there's our boiler size. So what does this formula look like here? It's 36, that is the volume of water in my indirect. 65 is the difference from my water entering the home, going into my indirect on the cold side. 115 is the target temperature I want going out to my hot water faucets. So the difference between 50 and 115 is 65. So 65, and then we got 500. That's part of our universal hydronic formula. So it's 36 is the size of my tank. I'm going to multiply that by 65. I'm going to multiply that by 500. I'm going to divide that by 100,000. That tells me on 50-degree water coming in to get my tank up to 115 degrees to be ready to support the home, that should take 11.7 minutes with a 100,000 BTU boiler. Everybody with me on that? That means my boiler is 100,000, my piping has the ability to carry 100,000 BTU, and I have the proper circulator size to drive that indirect to the capacity that it's capable of. What is that number? Well, a 40-gallon indirect, a good 40-gallon indirect can absorb probably around 150,000 BTU. Okay, you get a 119-gallon indirect, a good one out there, you'll probably absorb about 350,000 BTU. So I know this is only a 100,000 BTU boiler. Let's say I'm an 1.25-inch pipe or 1-inch pipe. I'm right on the edge. I have to have a circulator on there now that has the ability to deliver that flow rate of 10 GPM to that indirect, and that indirect has a coil inside of it that has the ability to absorb that 100,000 BTU, and will exchange that energy, and that would take 11.7 minutes, right? Yes, sir.
Just one more time with that formula, please.
Oh, we're going to do several because they're going to do some math here in a minute.
Oh, great.
Yeah, it's awesome.
All right.
So,
I think maybe the gentleman wasn't sure where we went from 40 gallon to 36.
so every manufacturer, they can list a tank at 40, but when they build the tank, it only has to be 80% of what they tell you it is.
Really?
Yes.
80%.
Yeah. So here we have a 40. You take a percentage off it. That tank actually holds 36 gallons. Yeah. So that's what we can do here. This one here is down 10%. So this one's only down 10. Indirect's down 10. A lot of water heaters, 40-gallon water heaters, you'll be down, 10, 15, 20% of listing. So that's where that number comes from. All right. Everybody good with that formula? If not, let Jim know, because I'm going to throw some numbers at you here, and you have to send some answers into Jim. We're going to stick with the same size tank because that's what we're going to do. Okay? I want to deliver 120-degree water to my sink, so that 115 will be replaced with 120. Still going to leave 50-degree water incoming. Could be 40. We're here in the Northeast. Could be 40, but most common, we'll call it 50. Going to leave the 500 the same, but you're going to take your boiler size, and you'll understand the method to my madness here in a little bit. You're going to make that 40,000 BTU. I want you to work through that, and I want you to start sending Jim answers.
Write that on the board.
Right there, 31.5. 31.5 is the answer. All right, so I'm going to roll this little boiler out of the way real quick. Put it here. All right, so we are looking at 36 times 120 and 50 in here, in our parentheses, right? That's what we got. And then got 500 over here, and we're going to divide that by 40,000. That's your boiler. This is incoming water temp. This is supply water temp. Okay? So somebody shoot Jim the answer. What's the difference between my 120 and 50?
They all got the right answer.
They got the right answer. So it would look like this. 36 times 70 times 500 divided by 40,000. What's my answer, Jim? 31.5 minutes. All right, I got another question for you guys. Anybody know why I used 40,000 BTU? Why would I use 40,000 BTU as a boiler size? Nobody sells 40,000 BTU boilers. Why would I do that? And we're in a hold pattern.
A couple of guys are getting it.
What are they telling you?
3/4 piping.
3/4 piping. How many indirects out there do you see that have 3/4 piping, and more than likely they have a zone valve? And we'll talk about zone valves over the next 3 weeks, but let's say it's a brand H zone valve that moves 35,000 BTU. That means you're moving 35 to 40,000 BTU worth of BTU to that indirect, which means it's going to take 31.5 minutes to recover. I hope this answers the question why I can only get 2 showers or 1.5 showers out of my 40-gallon indirect. Because I have a 3/4 zone valve on there, and it takes me 31.5 minutes to recover that tank. Does that make sense to everyone? Has anyone experienced this? Shoot Jim an answer. While you're shooting Jim some answers, I'm going to run you through another one. Okay? $36 times. Got 140 degree temperature we're looking for. 50 degree incoming water. Times 500. And we're going to drive this with 150,000 BTU boiler. Okay? So somebody send Jim the answer to this one. 36 times what? Times 500 divided by 150,000 BTU. What's my number here?
Oh, they're getting it.
What is it?
Well, I mean, they finished the whole.
They did. All right. So they know that this is 90.
Yeah.
How long did it take to make hot water, Jim?
10.8 minutes.
That's pretty standard. If you pipe and plumb and you have a boiler that can drive an indirect to full capacity, you'll make hot water in usually less than 15 minutes, 12 minutes, let's call it. So that is a recovery time chart. Hopefully this is another tool that you have in your toolbox. If you need it, it's there. Use it, take a snapshot. It will apply to almost everything. A 40,000 BTU tank style water heater. That was another reason that I used 40,000 BTU. If you have a 40-gallon standalone direct fired water heater with 40,000 BTU going in it, you can use the same calculation to figure out why they're running out of hot water.
That was actually a question that just came in.
Yep.
Then another gentleman had a statement that goes, that's why factory manifolds are 1 inch for the indirect.
They are now.
They are now.
Years ago, they were 3/4.
Yeah.
But even at 1 inch, you heard me say that a 40-gallon, a 45-gallon good quality indirect can absorb 150,000 BTU. 1 inch pipe, we said, only moves, let's call it 80 to 90,000 BTU, right? Let me just grab an eraser. I'm just going to show you something real quick here. All right, so I'll just get rid of this. And as you can tell, I'm not an artist, so bear with me when I make this next drawing. So here's that indirect tank that the gentleman was just speaking about. And we have tappings in the side. And I'm going to do it with one line because, again, I'm not an artist. This is 1 inch, right? That's what he just said. So this comes into the tank. and it does this. And then it goes back out of the tank, right?
It's very artistic.
Yeah, please. Phew. Hope you guys can understand that, but anyway. So this can absorb 150,000 BTU. So back to your pipe chart, what size, or get me real close, what size would the piping here from the boiler, the heating plant, what would it be? Somebody will see it in a minute, but I'll tell you it's 1.25 inches. And then when you get right here to this point, this is where your reducer would be. Okay? There, 1.25 inch pipe. Again, terrible drawer, but you get it. So how can I take the flow rate and the BTU from 1.25 inch pipe, neck it down to 1 inch, and not create velocity noises?
Very carefully.
I don't know. So we're not making 90-degree bends inside of that tank. So what they've done is we're making circles in here. So we're not going to hear the velocity noises because we don't have that 90-degree bend, right? And in addition to that, we're sending, let's call it it's 5 feet away. Let's say we're getting 145,000 BTU over to it because we have the right size circulator. This coil can absorb 150,000 BTU. Well, it's only 1 inch pipe. So what do? They add a couple of additional wraps in that coil so we have enough surface area to absorb the additional energy of the 150,000 BTU, and our cold water, whether it's coming in from the top, dropping down, running across coil, heating up, and then being drawn out to the house, that's what's going on with inside that indirect. So hopefully that makes some sense out of it for you, but the coils will be just a little larger.
So 2 questions came in, and it's jumping ahead.
Okay.
Basically, they want to know, how do you size the pump?
How do you size the pump?
Yeah.
That'll be
Yeah, thanks.
Jimmy. How do you size the pump? You need to understand the hydraulic friction of this coil. So we call that head loss. And you would need to know the BTU capability of that indirect, that coil in that indirect. Once you know the head drop of this coil and you know the BTU of the indirect, that will get you going down the road of circulator sizing. And here in a couple slides, I'm going to show you some curves, not to teach you 100%, but just to start to plant the seeds. So over the next 2-3 weeks, you will be sizing circulators over the next few weeks. We want you to leave here with the confidence and capability of sizing circulators when you finish this course. So I'll keep rolling, Jim. If they keep coming in, please fire them out.
Yep.
Chris, I think I lost my clicker. Hey, look at that. So here we just threw up some boilers on there just so you can see some near boiler piping. We'll dive into this a little bit more throughout the next few weeks. But here's primary, secondary. Again, we're going to hammer this home. Here's a list of ECM circulators that are out there. Okay, so we're going from residential all the way to commercial now. These are circulator charts. This one's clean. Let me go to the next one. This one right here, this shows you the ability of a circulator to, make these changes as we call them holes in the system close. So as zone valves close, that's closing a hole, all right? The more zone valves are closed, the more holes closed, the more we're going to adapt and adjust the flow of that circulator to marry up to the system, okay? And this right here just shows you what I talked about earlier with an ECM circulator. Here at 100%, that's 10 volts, and it works its way all the way down to 2 volts and 4 volts and so on down the line. That's what's going to change automatically on an ECM circulator as it's running in comparison to an AC-driven circulator. So just so you have a heads up going into this as to what you're looking at. Darn it, I hit the wrong one again. There we go. So some of the manufacturers that have made a change to the 007E, you can see them on the screen. So you'll be running across these circulators a little bit more often. And this is the curve of a 007. 10 feet of head, out to about 8.25 gallons of flow, it will stay at 10 feet ahead. Once you get to beyond 8.25 gallons, it does flow water all the way out to 16 gallons a minute, but that would be at 0 feet of head. So what you will learn over the next couple of weeks is I need to know the head loss of a heating circuit or of that indirect, and then I need to understand the flow rate in order to drive the BTU. So I'm going to ask a question here. If I have 10 feet ahead, and I need to move 60,000 BTU, what would my flow rate be across here? And will that circulator handle that demand? Send those answers into Jim.
What'd you say, 6 GPM?
6 GPM, 10, oh, you gave him an answer. 6 GPM. Jim's on your side, people. Jim is on your side. So yeah, 6 GPM, 60,000 BTU, and it just comes automatically. It just comes automatically. And hopefully by the end of this course, it'll be automatic to them. You know, I always joke with Jim. I walk into a boiler room, I'm looking at the near boiler piping already, and I'm calculating in my head, oh, there's two 3/4 zones. That's 80,000 BTU. So that's kind of what we do. And I think we're right near the end here. I want you to understand. So we took a circulator apart, and we want you to see exactly what goes on. So whether it is this 007 or the 007E, it doesn't matter. This is the eye. So the water runs in through the eye when you first fill the boiler, and when it goes through the eye, it comes in and fills this little chamber up here. So you always hear the term wet rotor circulators. That's what they're saying. And this is our 007E. So the water comes in on the front side of this through the eye, goes through this little, looks like a brass washer here. That's a bio barrier, black iron oxide barrier. Remember, ECM, we got a permanent magnet here. So we fill this up. That becomes the water cooled area. And the reason for that bio barrier is we know we have, magnetite and all different metals in our heating systems. So we want to make sure that magnetic junk, basically, that's floating around the system does not attach itself to our permanent magnet here. This goes in, and then it's driven by pulses, and we pulse around to drive that magnet, and that's what tells this unit to rotate. So that is what a wet rotor circulator looks like. So when we refer to a wet rotor circulator throughout the next several weeks, you will understand what that terminology means. So week 1 was kind of a get you up to speed for week 2, 3, and 4. We did do a couple of formulas, which are going to be important to you going forward. Please review your material. Again, have a pen, paper, pencil, calculator, cell phone, whatever you need in front of you. Download a day ahead of time the floor plan so you have something to work off of for next week. And your TACO, in your handouts that we sent you, which again will be on the left-hand side or right-hand side of the screen, go down. There's takeaways that we put in there. You're probably going to want to print this out. If you don't want to print out the whole book, it would be really good if you print page 48. And 49 would be really good to print those two minimum. If you print 48 and 49, and then you will need page 55 and page 51. If you print those 4 pages, I think you have enough to get by, because we're going to use some of those the circulator curves that are on those pages. So instead of printing the whole thing, those 4 would be really, really good. Have those handy. You'll be leaning on them heavily throughout this presentation.
All right, so 2 things. One gentleman's saying, when did we send out the books? So it would have been a download on today's.
It's right in the handouts.
Yeah, it's right in the handouts.
Right.
So look on your.
Chris, will they see it if you open yours up? You guys may see.
Only you see my screen.
Oh, only I see your screen. Okay. All right. Yeah, so they won't see it. But on the right-hand side of the screen where you have that little arrow, pop that little arrow, open that up, scroll down to the bottom. You'll see questions, and then you'll see handouts. You're going to go into the handouts, and there is, in the handouts, there's the 4-week, there's a residential, this guide, there's a zone control wiring guide in there. There's 3 different documents that are in there. Please, if you can download them, it'd be great. Even if you have a second computer, you want to put them on a jump stick, whatever you want to do, you're going to need those.
And then 2 gentlemen want to know, can they review this? So this is recorded.
Yeah, right. It'll be recorded. So
Right.
you can go to wellsdarby.com and go to our training page, and you'll see this recording in there if you need to review it. If you're really stumped on something and you need to reach out, I have a lot of windshield time. 908-300-1576. My email is there. Jim's email is on the screen.
Yeah.
Reach out. We're happy to help. We are very busy, I will say that, but we'll get back to you and help you. And we always ask before we start the next session, do you have questions from the week prior? So we want to get those out of the way before we start. And normally we clean those up. And then we dive into session 2, 3, 4.
Please come back next week because you guys are awesome.
Yeah, please. Yeah, that was a great conversation back and forth. We really appreciate it. We try to do these live, but some people will let us in, some won't. Be happy to do this live with you guys if needed. But thank you everyone for attending. We will see you same time, same bat station next week. And you'll see Jim's pretty face instead of mine.
What's your phone number again?
908-300-1576.
That's it.
Okay? Thank you, everyone. We appreciate your time. See you next week. 28 seconds.